Welcome to Differential Equations. In our first lecture, we're going to give an introduction to differential equations. We're going to cover what they are, where they come from, and where you might have encountered them or will encounter them in your other courses. So let's go ahead and get started. And we're just going to start with a very simple question. What is a differential equation? And the answer we'll give, keeping it very simple, is it is an equation involving an unknown function and its derivatives. So let's introduce some notation that will be standard for our course, a mathematics course. So we're going to think of usually y as being a function of x. X we're going to think of as the independent variable. And then we have these different notations for the first derivative and second derivative of y, the function. Y prime and y double prime are a little bit more convenient to write. The differential notation, dy over dx, that'll be useful for other topics that we'll see later in the course. So just make sure you're comfortable with the notation. This is going to be what we stick to for our entire course. If you look at any other resources on differential equations, they might have a physics or engineering perspective, in which case you might see the following notation. So instead of thinking of y as a function of x, you might encounter the position x as a function of time. So we would consider x as the function, the position function, and then t for time would be the independent variable in this setting. All right, and the derivatives there you might recall from your previous calc courses, the derivative of position is velocity, and the second derivative of position is acceleration. All right, so we're going to stick with the y as a function of x notation. And here are some examples of what differential equations look like. Some of them are rather simple. For example, in example 1 there, and then as you progress down through 2, 3, and 4 there, they get gradually more complicated. Now, without even going into detail about what this subject is, differential equations, it's like what we do with all other equations, try to solve for something. But since our unknown is now a function, we're not solving for instance, x representing a number. We're going to try to solve for y, which represents some function of x. All right, and that is our goal. So differential equations, in our notation, we're simply going to try to solve for y. Now we're going to give some motivation, which will come back to this notation, which we'll see in a few moments. Okay, so for our introduction, for part 1 here, we're going to focus on some motivation for the subject. And there's a lot of different ways you could approach it, from mathematics, from physics. So we'll start with maybe an answer coming out of Calc 2, prerequisite for this course. And one way to get to differential equations is by generalizing antiderivatives. So we're going to take the idea in Calc 2 that you learned about and elaborate it on antiderivatives, and then see how with a modification, what we'll call a generalization, how we get to differential equations. Okay, so let's go back to Calc 2, and let's say we have this statement or equation, y prime equals f of x. So f of x, that's just some function of x. All right, now what you might recall from your Calc 1 and Calc 2 course, you can kind of switch back and forth between these two statements in equivalent but different looking notation. So we could write this statement using derivatives, y prime equals f of x, or we could write it using integrals, antiderivatives, as y equals the integral of f of x, integrating with respect to x. All right, now on the right side over here, what that is asking us to do is to find an antiderivative for that function f of x, which that's pretty much what you spent kind of the very end of your Calc 1 course on, with some basic antiderivatives. And then probably quite a lot of time in your Calc 2 course was on that, finding antiderivatives. All right, so what we're going to do is look at this the statement written in derivative notation, we're going to look at that as a very simple differential equation. So we have y prime equals some function of x, and our goal is to solve for y. Now, if you just look at the notation above, it basically shows you how to get y. How do you undo a derivative? Well, we're going to integrate. So if that is our differential equation, y prime equals f of x, what we're going to call our solution for y, it's the integral of f of x, whatever that comes out to. Let's take a look at a really simple, concrete example. Let's say our differential equation is y prime equals 2x. Now, just building off of your Calc 1 and Calc 2 knowledge, you can probably answer this. Pause the video if needed and give yourself a few seconds to see if you can figure out and solve for what the y, that unknown function, is, such that its derivative, y prime, equals 2x. We'll check in a few seconds. Welcome back. Hopefully that was pretty simple. This is very conceptual. The calculation shouldn't be too bad. So to solve for y, we undo the derivative. We basically integrate or find an antiderivative for that function of x on the right-hand side, 2x. And if you integrate 2x using the basic power rule for antiderivatives, you'll end up with y equals x squared being the antiderivative of 2x, and then plus c. And that is our first way to solve a differential equation. We have our solution, y equals x squared plus some constant, and that is the solution to that differential equation, y prime equals 2x. Now, again, this was really simple. This is kind of taking the end of Calc 2 to transition us to differential equations. So we briefly mentioned the idea, which will underlie our entire course. We're going to undo a derivative or derivatives by integrating. And that probably makes sense from your Calc 1 and Calc 2 course, integrating and differentiating their opposites inverse operations. All right, now this notation is what you saw pretty much all through Calc 1 and Calc 2. Y prime equals f of x. I want you to notice for that differential equation, the right-hand side only depends on x. That's what being a function of x means. F of x, that right-hand side only contains x's, no y's. Well, often in mathematics, what we do is make a small modification, and here, the right-hand side only depends on x. We're going to generalize, and let's ask the question, what if the right-hand side also contains y in addition to x? So we could say the right-hand side is now a function of x and y. What effect or change does that have now? All right, so let's take a look at an example. So instead of y prime equals on the right side only x or a function of x, let's say we have here y prime equals now a y. So for our differential equation here, the first one by generalizing that we'll take a look at, let's say is y prime equals y. Now our goal with solving this differential equation is we're going to look for a function y whose derivative y prime equals the original function. Now we probably don't even have to do any mathematics to solve this. I think from a solid understanding of Calc 1, you could tell me a function y prime where the derivative is equal to the function. And that would be e to the x, right? What's the derivative of e to the x? Itself. So y equals e to the x. That is a solution to this differential equation. Now, that's just building off of your knowledge of derivatives from Calc 1. In a little bit, we'll see how we can solve in a systematic way this differential equation to arrive at that solution y equals e to the x. But that's something for kind of the next topic in our course, not for our introduction. All right, let's take a look at some other generalized examples. So statements here that are no longer just antiderivatives, since this example in example 1 has a y on the right-hand side. All right, and here are some others that where the right-hand side contains a combination of x and y. Notice in example 4 there, we kind of still have something a little bit different. No longer is there just stuff on the right-hand side. We have it replaced with 0, but now we have, in addition to a derivative of y double prime, on that left side, we have y double prime plus y. So in example 4 there, it already seems a lot more complicated. Now I'm going to try to convince you, like example 1 at the top there, that you know functions that are solutions to example 4 there. Let's rewrite that differential equation. That's going to be what we define in a little bit later in this intro as a second order differential equation. Example 1 is what we would call a first order differential equation. Notice example 1 contains y prime, a first derivative. Example 4 contains y double prime, a second derivative. So let's rewrite example 4, and I'm going to convince you that you know functions that are solutions to this. So what you want to think is, do you know any functions for y is a function of x, where you twice differentiate and you get the negative of the function? Pause the video, see if you can think of that. We'll check in a few seconds. All right, welcome back. I'm confident you know the solutions here. Functions that twice differentiate to the negative of the function. And the solutions here are sine and cosine of x. If you twice differentiate sine, you'll get to negative sine of x. And if you twice differentiate cosine of x, you'll get negative cosine of x. So what we have here is another differential equation where the solutions we already know. Now, as it turns out, it's going to take us quite a bit of time to be able to solve in a systematic way example 4, but that's going to be something we'll get to later in the course. All right, now all these examples generalize the concept of an antiderivative, and that'll be one way that we can start to get access to our course, going from the end of Calc 2 to the beginning of our course by generalizing antiderivatives. All right, now just to kind of see for some of these examples, if the right-hand side only contains x, for something like y prime equals a function of x, pretty easy to solve, you just integrate. What we've been seeing in examples 2 and 3, and possibly example 4 there, they're a little more complicated. Now the right-hand side might contain x's and y's. And if that's the case, that requires other methods, which we'll learn throughout our course. All right, so that's motivation topic 1, basically generalizing antiderivatives. Let's take a look at a second way to motivate differential equations. And the second example I want you to think is that it solves mathematical problems. Now, we're going to take a little, I guess, step into mathematical history. And one of the first times that differential equations was used to solve a mathematical problem, so shortly after the development of calculus, came what's called the Brachistochrone problem. And it's referring to what's called the curve of fastest descent. So you might refer to some of your Latin root words there, crone, that refers to time. All right, so let's kind of flesh this out in a little more detail for what is called the Brachistochrone problem. All right, so it's pretty simple. We're going to have a starting point and an end point, and basically we're going to release an object such that it travels along a path, and what we want to do is find the path so that it reaches the end in as small amount of time as possible. So if we were to state this as a concrete problem, we're going to say we're going to try to find the path of an object moving without friction. So it's moving along some curve with no friction, but under the effects of gravity that minimizes the travel time. All right, so we're going to think of just drawing a curve that an object is going to roll along such that it minimizes the travel time. Now, one possible curve, which is not really a curve, it's just a straight line, is this, going from the start to end point in a straight line. Now, this does minimize something, but unfortunately, it is not the answer to our problem. A straight line is going to minimize the distance traveled. So this minimizes distance, not the travel time. What we have to take into account, even though there is no friction, the gravitational acceleration is going to pull the object down along that curve. We want to try to exploit that to see if we can kind of travel along that curve in a little bit quicker of a pace than along a straight line by making use of the gravitational acceleration downwards. Now, this is actually hard to sketch by hand, but the path, it's not quite circular, it's not quite a parabola. The shape is what's called a cycloid, and that is the path that if you release an object, that minimizes the travel time. Once we go through and kind of complete this lecture, I'll make an announcement through Blackboard that shows you kind of a nice little video of how that path actually minimizes the travel time compared to a straight line and other curves. You'll see in real time an object move along the curve, and then the one moving along the cycloid reaches the bottom first. All right, now how do we relate this back to differential equations? Well, the equation for the curve, which we see on the screen there, the cycloid, the equation for y as a function of x that describes that curve comes from solving this differential equation. The c that appears in there, it's some constant, not important for our lecture right now, but this is a differential equation where if you solve it, if you solve for y, you get y as a function of x that describes the path for the curve of fastest descent. The brachistochrone problem, it's one of the first times historically that differential equations was used to solve a mathematical problem. All right, let's take a look at a third motivation, and a standard place for differential equations to come from is physics. So our kind of starting place for physics, thinking of maybe some courses that you took recently or will be taking, is Newton's second law, F equals ma. Now we're going to keep this really simple. The force F and acceleration A should be thought of as vectors. We're going to ignore that and just consider one-dimensional motion. So for instance, an object just moving along a straight line, we won't consider any movement in 3 dimensions. All right, so let's recall some notation. If we are thinking about position, let's denote that by x as a function of time. So x will denote position, and then quantities related to position would be velocity and acceleration. And again, from a good Calc 1 and Calc 2 course, you know these relationships. Velocity, you can say it's the first derivative of position, and then acceleration, it's the first derivative of velocity, or acceleration is the second derivative of position. Think of it as starting at the top with position. Each time you move down, you do so by differentiating. All right, so what I want to try to convince you is, despite what you might have learned in your physics course, Newton's second law can be thought of as a differential equation. Let's take a look at those two versions for the acceleration. A equals v prime and A equals x double prime. Now, if we replace A in Newton's second law with these two different expressions, we get two very different differential equations. The first version, replacing the acceleration with v prime, is what we're going to call a first order differential equation for the velocity v. The second version, replacing the acceleration a with x double prime, we get the differential equation f equals m times x double prime. That can be thought of as what we'll define as a second order differential equation for the position x. Now, the reason why you might want to have two different ways to think of Newton's second law, either as a first order differential equation or a second order differential equation, is that it depends on the forces involved. Some forces depend on the velocity of an object, like air resistance. Some forces only depend on position, like the spring force for Hooke's law. All right, we're going to use that as an example. This is all way beyond the scope of our short introduction here, which we'll go into more detail later in the course with applications. Just to get to a kind of point to move us through to the next topic, let's go into a little bit of detail with Newton's second law thought of as a differential equation. And we'll tie this back to some examples that we covered earlier in our first motivational topic, generalization of antiderivatives. Okay, so the example here, we're going to consider the system of basically an object of mass m attached to a spring. And the force for a spring, what's called Hooke's law, the force equals negative k, where k is what's called a proportionality constant or spring constant, and then times x, where x is the displacement of the object. All right, now I'm pretty sure you know what's going to happen if, for instance, we take that object of mass m with no forces acting on it at rest. It's just sitting there at its equilibrium position. And then imagine if we just displace that mass and then let go. So we know if we displace and then let go, it's going to start oscillating, right? So we can kind of have an expectation of what solutions should be for x as a function of time. What mathematical functions describe oscillation? Sine and cosine, trig functions, right? Now, if we take the point of view of solving a differential equation here using Hooke's law in Newton's second law, we should get that, exactly a differential equation where sine and cosine are solutions. Let's see how we can do that. So we're going to use for the force, the only force acting on the object, the spring force, negative kx. We're going to replace that on the left side of Newton's second law. The only force acting on our object here is just the spring force. And if we plug that in, we get the following differential equation. Negative kx, that's the only force acting on the object, equals m times x double prime. Now, to tie this into our first motivational topic, let's rewrite this differential equation. So what you can do is basically add kx to the right side, and then you can divide by m. And if you do that, you should get this differential equation just rearranging algebraically. X double prime plus k over m times x equals 0. All right, now let's keep in mind here, we expect to get sine and cosine as solutions to this, since we know if we displace that mass and then release it, when it's attached to a spring, it should oscillate back and forth, assuming no friction to slow it down. All right, now let's go back to a second order differential equation that we encountered. In different notation, here we're thinking of the position as being a function of time, t, but earlier we saw this differential equation in red there for y as a function of x. Now ignore the different notation. Above, we're thinking of x as the function, and then below in red, we're thinking of y as the function. Now earlier in the first part, the first motivational topic, you kind of saw, I hope just from your knowledge of derivatives, that sine and cosine are solutions to that differential equation in red. So we would say to that differential equation, solutions are sine of x and cosine of x, which is what you would expect for things that oscillate. Now compare the differential equations. They are pretty similar in structure. You have a second derivative, and then you're adding to that the function. But in the version that we're looking at, you have the function x being multiplied by constants. Trying to think of the constants as being insignificant right now. Hopefully you agree those two differential equations look similar. You have a second derivative term, you have a function term. If the one in red has sine and cosine as solutions, shouldn't be a surprise or too much of a stretch to think that this differential equation also has sine and cosine in some form as solutions for x. And as it turns out, that is correct. We're going to save the details for later, just keeping this very informal for you to make some connections. All right, and again, this is what we expect if you displace the mass and then release it. We should expect the position to oscillate. Oscillatory patterns and functions are described by sine and cosine. Okay, now let's tie this third part, physics, which is basically Newton's second law, can be thought of as a differential equation. Let's tie this into a fourth motivational reason or topic. Differential equations allows you to make some insights and predictions. Now, I like the spring system that we just talked about because it's very simple and you can actually see what's going on. If you were to displace the object attached to the spring, you can actually see the mass or block, whatever it is, oscillate back and forth. Now, what we're going to compare the spring system with is another system, an electrical system, a circuit, with something called an LC circuit. L is going to refer to inductance, and C refers to capacitance. All right, now of interest to the spring system, we'd like to know what happens to the position of the object as a function of time. So our goal in the spring system, which we briefly looked at previously a few moments ago, our goal was to solve for x as a function of time. So here, we're going to try to think of getting a differential equation for the position x. Now, we did see that moments ago in a little bit of detail. We didn't actually solve it mathematically, but at least we made enough connections. For many of you who haven't gone through a physics course dealing with circuits, electricity, and magnetism, you may not know or have any idea what happens in an LC circuit to the current. So in the spring system, we want to know what happens to the position as a function of time. In the LC circuit, we're interested in knowing what happens to the current as a function of time. All right, now there's a lot of detail, which is all best left to a physics course. I just want to touch on how we relate this to differential equations. All right, so we saw in our third motivational topic, getting to physics, Newton's second law as a differential equation, and then finishing with the example of Hooke's law, we did see for the spring system that the position should have sine and cosine as solutions. We did that by comparing it to a very similar differential equation from part one. All right, the question we're going to ask for the LC circuit, the different system, where you might not have any idea what happens, we're going to ask what happens to the current in an LC circuit. So for instance, if we were to turn the circuit on, what happens to the current as a function of time? Okay, now for the spring system, we arrived at our differential equation by applying Newton's second law. And we have this differential equation there, which we saw earlier. For the other system, the LC circuit, you apply something called Kirchhoff's law. And again, beyond the scope of our course, you might have encountered that in your physics courses. If not, don't worry about it. If you follow both of those through Newton's second law and Kirchhoff's law here, you get these very similar looking differential equations. Now, some of the symbols are different. On the left, for the spring system, x is our function of time. On the right, I is the current as a function of time. But aside from the names of variables, these two differential equations look remarkably similar. You have a second derivative term, you have a function term, and the function is multiplied by constants. M and K are both constants, the mass and spring constant in the spring system. L and C are both constants in an LC circuit. Now, the point that I'm trying to illustrate here is due to these differential equations being remarkably similar, we should expect similar solutions, similar mathematical functions that solve both these differential equations. Now, on the left, we did see that sine and cosine are solutions for the position. And since those two differential equations are so similar, we should expect sine and cosine functions as solutions for the current. What does that tell us? If the current has sine and cosine in it, well, that tells us that the current oscillates. There's peaks and valleys, it increases, decreases over time in some regular pattern with a certain period and frequency. And again, you might not have known of that if you were to have taken a look at an LC circuit, but the mathematics guides us to this prediction. The question being, what happens to the current in an LC circuit? The prediction, which we get by solving a differential equation, the prediction is that the current oscillates. All right, now all these topics between the four examples for motivating differential equations, these are all things that we will touch on in more detail later throughout our course. So there's some aspect to differential equations as being a generalization of antiderivatives. There's all sorts of kind of relationships to physics, and we will continue to build on that with applications as we go through our course. So that's it for the first part in our intro, some motivation for differential equations. In the second part, we're going to get to some of the classifications and different types of differential equations.